this section, we are going to learn about radial acceleration. So I have drawn here the Sun and the Earth orbiting around the Sun. So the Earth is going to follow this circular path around the Sun. Now the Earth has some tangential velocity, and if the Sun were to disappear, the Earth would travel in a straight line. However, the Earth does not travel in a straight line, it travels in this circular path here. And the reason it does so is because of a force from the Sun. So the Sun exerts a force on the Earth, which causes it to travel not in a straight line, but in the circular path, or in an orbit. As the Earth then orbits around the Sun, we find that the velocity stays the same, but changes direction. So you can see that the velocity tangent to the circle changes direction, but we're going to assume a circular orbit where the velocity stays the same in magnitude. And the force from the Sun on the Earth is always going to point towards the Sun, or towards the center of rotation. So this means we need to talk about acceleration a little bit differently, because as I said, the magnitude of the velocity remains the same, but we can see that the arrow is pointing in different directions. So we're going to define the difference between tangential acceleration. This is going to cause a change in magnitude of the velocity, so change in size of the velocity, versus a radial acceleration, which is going to cause a change in direction of the velocity. So the scenario we have set up here with the circular orbit is that the tangential acceleration is 0. We're assuming that the magnitude of velocity change stays the same. But we have this radial acceleration causing a change in direction of the velocity. And the radial acceleration is going to point in the same direction as the force. So we have a radial acceleration that's going to point in the same direction as the force, causing that change in direction, which in our example here is the force from the Sun. Now we have to be careful here. This is not a new type of force, it's a new direction of force. So the force that the Sun exerts is going to equal the net force in the radial direction. So essentially we have a third option for Newton's second law. So you do net force in the x, net force in the y, net force in the radial direction now. So just like we saw with x and y, the forces that we're summing to get the net force change from problem to problem, but they still sum to the net force in a particular direction. So Newton's second law remains the same. So we're going to say net force in the radial direction is equal to mass times acceleration in the radial direction. Now when we did acceleration in the x, acceleration in the y, we did not go back and explore further with this, but that acceleration we're solving for could have been plugged into one of the kinematic equations, and we could have used that to find velocity and displacement if we wanted to. Here though, acceleration is not going to get plugged back into a kinematic equation, but we have a separate relationship for radial acceleration. So radial acceleration is going to equal the tangential velocity squared divided by the radius, or the distance between the two objects. Or we can rewrite it in terms of angular quantities, which is r times the angular velocity squared. So we would use the same procedure as before, where you would sum the forces acting in the radial direction and set them equal to mass times acceleration in the radial direction. We just have a separate formula for how we solve for acceleration than the ones in the kinematic equations.